Okay, getting started. Now, if I remember right, Chris, you said you won't be here on Friday because of, or actually, you guys don't have school on Friday. Is that correct?
Right.
And
I won't be here on
you won't be on Wednesday. Hey. We've got to figure out a way to make up for the class I missed, make up for that class, because
I would be here, except I'll be in DC on Wednesday.
Yeah. And you gave me plenty of warning. It's not like it's the last minute thing. Well, we clearly won't be having the test on Friday because you won't be here on Friday. And so let's, Indy, why don't you and I still come together on Wednesday and just, we can, do a review of what we've learned type of stuff to just help you out. I mean, obviously it'd be good for Chris too, and Chris can watch the YouTube thing. And then we'll plan on having the exam on, I'd like to do it on Monday following break. Does that work for you?
Sure. You can do it.
Okay.
Make it happen.
Okay. So today what I'm going to do is look at, number one, the full out solution for the particle in a finite well, right? We went over it before, and we had some question. I said I would work it out for you and post it. And then, of course, after class, I got ready, went to California. We had the red eye back. I actually was finally able to do something useful from 5 last night, and I worked until midnight last night getting all this ready. But yeah, so I'm going to go over that finite square well problem with all of the gory math here. And then I'm going to move on to the homework problem number 4. Indy had asked if I could, make a YouTube video showing how you do the solution. So I figured I'll do it in class, because that way we can make sure that you get the full and can ask me questions as we go through. So pretty much everything today is review and should help drill in some ideas. I was going to ask you a quiz, but once again, I didn't have time to ask you. I was going to make a quiz. And I would tell you what the questions would be, but I'll just fold them into the test. Because I have one that I know I would be. So here's our situation, a figure of what the potential situation is. How is this applicable? Well, this is a reasonably good first order approximation for a nucleus of an atom. Right? You have inside the nucleus of an atom, particles have a fairly constant potential. If you were to get out, it would go to 0. It's obviously not square. It's going to have walls that go up and then come down. Since I can't write, I can't draw it on there, but come down with a exponential decay as you move away. But it's a reasonable first approximation. And so as we go through the problem, note that we're using a total energy E, where E is going to be a negative value. It's going to be a bound state. So the energy E is going to be somewhere, there's nowhere where I can use hand signals, somewhere between 0 and minus V0. So V0 is a positive number. The potential energy inside is negative value, so minus V0. E is a negative value. It's the energy that we actually have. We have to solve it in 3 regions, region 1, region 2, and region 3 is shown with the red Roman numerals. So in region 1, because our potential is 0 outside, the Schrodinger equation is the very simple form that gives us an exponential result. And so our total solution, and you notice I has the form of psi 1 is equal to e to the bx. Right? That you can use whether you have differential equations or not. The solution has that form. You take its second derivative, which is just b squared times psi. You substitute that in for the second derivative, and you have minus h bar squared over 2m b squared times psi is equal to e psi. I rearrange that so it's equal to 0, which gives you 2 solutions. Either the thing in parentheses is 0, in which case, well, that's the one we explore, or psi is 0, in which case we have no solution. So we throw away the trivial solution and say, let's solve for what happens if the thing in parentheses is 0. And so we make a new constant that is kappa, which is the square root of minus 2me over h bar squared. The minus sign is there so that we have the square root of a positive value. Since the energy E was negative, that's going to be square root of a positive. So kappa is a real positive value in our solutions where B is plus or minus kappa. When you have two solutions, then your total solution is going to be a linear combination of those two. So some constant times solution 1 plus some constant times solution 2. So our solution here is going to be A, constant 1, e to the minus kappa x plus B, constant 2, e to the plus kappa x. And then we immediately say, okay, we have a rule. Those are correct solutions to my equation. But if it's going to be a solution to the Schrodinger equation, it needs to approach 0 as x approaches plus or minus infinity. If it doesn't approach 0 as x approaches plus or minus infinity, it's not normalizable. We have a real problem. So to be a solution to the math, that's it. To be a solution to the physics problem, the quantum physics problem, we're going to have to insist that the constant A is 0 or it can't be normalized. And so that gives us our simplified there. There's our solution in region 1. Then in region 2, well, now we have a potential, so my Schrodinger equation becomes the full thing. It's a constant potential, so it's not too difficult. And so with that constant potential, I'm not sure why there's an I there. I know I was trying to put Roman numeral 2, and I must have missed and not hit delete when I moved over to put it in. So that I should be gone. I really wish, well, let's see. Will this allow me to? Yeah, kind of. There, now I obscured it with my finger. With me? So I can kind of write. So the same form, put that in, rearrange it to collect terms, and I forgot to put the Roman numeral 2 there. Obviously, I copied from the first one and pasted in the second one and then changed appropriately and didn't get the Roman numeral changed correctly 2 places now. So that should be psi sub 2. So now I take this, and once again, either we have the trivial solution or the thing in parentheses has to be 0. So B is equal to, making the thing in parentheses positive. Okay, go away. I cannot, for the life of me, get that plus thing to go away. That will make it go away. So to make it so I have a positive inside the square root, I have to take the negative and bring it out as plus or minus I. Then I have square root of 2m parentheses e plus v0. We talked about in class last week that e is a negative value, but v0 is a positive value that's bigger. And so this is now a square root of positive, so it's a real. And here I went with the book very carefully. L is what the textbook uses for that square root of 2m parentheses e plus v0 over h bar squared. So we have, again, 2 solutions. Now it has imaginary solutions. So I have my exponential with imaginaries, and I wrote the solution 2 different ways. One with e to the ilx and e to the minus ilx, one with sine and cosine. Either one is fine and acceptable. I think it's actually easier if you don't apply symmetry rule to stay with the e to the form. If you can apply symmetry rule, it's definitely easier to go with sine and cosine. Then moving to region 3. Region 3 is exactly the same as region 1, so my solution is exactly the same as region 1, except to be normalizable, now x can go to plus infinity, so it has to be the term with the plus sign that has its coefficient 0, so the g has to be 0. So now we have the form of our solution, so I can rewrite my entire solution here. The solution has different values in the different ranges, and so I have the 3 different ranges. There's my full solution. What I don't have is the values of the constants and any kind of quantization rule. And so this is, I think all of that we went through with a reasonable amount of clarity and description. But any questions up to this point? No. Okay. Now we have to apply our boundary conditions. And we learned with the delta function why we have the boundary condition of a continuous slope unless we have an infinite potential energy function. And so we're going to apply those two conditions. Number one, that the wave function must be continuous. And number two, that the slope, that is the derivative, must be continuous. So the first one at boundary between 1 and 2, psi Roman numeral 1 at minus a, because that's where the boundary is equal to psi Roman numeral 2 at minus a. And then just substituting the two psi's, I get this equation. Then for the slopes, I take the derivative of the left side, evaluate at x equals minus a. The derivative of the right side, evaluate at x equals minus a. And those also must equal each other. So I put an extra line here so you can, actually to make sure I got my signs right, so I can show the explicit differentiation before I put in minus a for x. So the derivative of be to the kappa x is kappa be to the kappa x. So kappa be to the kappa x, and then the derivative of ce to the minus ilx was bring down the minus il, ce to minus x, and so on. Derivative of sine of lx, bring out the L, and cosine of Lx. Derivative cosine at Lx, bring out the L, and it's minus sine of Lx. So I had those, and then I put in for x minus a everywhere to get the bottom equation. So now I have two boundary condition equations. Okay, I'll use my fingers here. We'll see what happens. The two boundary condition equations are this one and this one. Understand the origins of each one of those equations. Okay, and if you see a mathematical error, I did do this late at night. Oh, shoot. In fact, later on, I admit, man, I hope I did that math wrong because I have not had much sleep. So now we go to the next boundary, the one between regions 2 and 3, and do the same thing. So now we get another new boundary equation. That one. There we go. This new boundary equation and this new boundary equation. So I have four boundary equations. How many unknowns do I have? Give me a number. Throw something out at me. Or name them.
So we have B, C, D, and F. That's 4.
Okay, so that's 4, except there is one more. I expected you to say 2 more, and I was going to say, you went too far. L and kappa are also unknown, but both L and kappa depend on the energy E. So there's really only one more. There's a total of 5 unknowns. So we have 4 equations. That's not enough, right? What's the 5th equation we're going to get? There's another equation we always apply. It's not coming to mind. I know that you both know it. The normalization condition.
Oh.
You've done that just a few times, right?
Of course.
So we have those 4 equations plus normalization that's going to allow us to, well, come on. I could have sworn I put my pen in my pocket, so I'm a little bit worried that it's not there.
Yeah.
There is no hole, so I probably set it down. So now we have to combine these, and the first, here you can see I said the 5 unknowns, since both kappa and L are proportional or functions of E. Here I rewrote the boundary conditions only using the trig functions. So only using the trig functions, here's my boundary conditions. And you'll notice I arranged the boundary conditions so that I have the 2 that were the function is continuous together, and then the 2 that were the derivative is continuous together because they look similar. And if I combine the first 2 equations, that is, if I add the 2, then the C sine LA is going to go to 0. And so if I add the 2, I'll get 2D cosine LA is equal to e to the minus kappa a times b plus f. Now that still has three unknowns plus the kappa and L, but I eliminated a C and replaced it with an F. And then I subtract the two and I eliminate the D term and get the C term. And then I did the same thing with the second two equations. And at this point, I said, well, the book wasn't half bad at saying we should probably apply our symmetry conditions. The book didn't go this far. The book said, let's take the fact that we have a symmetrical situation and only look at half of the problem. And I thought that obscures just a little bit what we're doing. So I wanted to get down to here showing the application of all the boundary conditions. The book took them out because the biggest work is the boundary conditions and then solving those equations. But at this point where I was in solving for the equations, I realized I really do need to apply our symmetry relation. That is, we have a symmetrical situation, which means that our probability density is going to have to be symmetric, or our probability, psi mod squared is going to have to be symmetrical, which means that my psi has to be either even or odd, that's symmetrical or anti-symmetrical, so when I take the mod squared of it, it's symmetrical. So looking at this, my solution in the middle region had a sine and a cosine. Cosine is an even function, sine is an odd function. My solution on the outside, I have a b and an f constant. If I have a symmetrical solution, the even solution, then I'm going to have b and f are equal to each other. If I have the anti-symmetric solution, b and f are going to have to be same magnitude, opposite directions. One's positive, one's negative. And so I said, let's just break it down into the two different solutions. So first looking at the even solution, the one where b is equal to f. B is equal to f, and c is going to have to be 0 because c is what corresponds with the odd solution, c sine of Lx. I should go back up to here. C is the one that goes with the sine with the odd solution. So if I set c equals 0 and b equals f, I had 4 equations that I had derived, but now I only have 2 unique ones. One of them is just a repeat. So these are the 2 unique equations I get. And if I take the lower one and divide it by the upper one, then I get, then I get this. So that is the result of my boundary conditions if I'm doing the even solution. Now notice I eliminated all of my constants except for I have the kappa and the L that depend on E. So this is where I actually fundamentally stopped my lecture before. We get to this equation and we're like, how do you solve this? It's transcendental. There is no way to analytically solve this and get a number. You just can't do it. So how do you solve it? You use a numerical method. So the standard numerical method for solving this is to define a variable z. Now you don't have to define a variable c, but you have to find a way to combine kappa and L. So define the variable z is equal to LA, and of course I substituted what L is to write that out in terms of energy E. And then we define z sub 0, which is what z would be if the energy was 0. So that's what the sub 0 means, is if the energy was 0, that's what I would have for z. And when you look at those, the first initial blush, at least for me, is that seems like an odd way to define these a variable and a constant. You know, what's the purpose of defining these? And the purpose is to make it easier to write that final equation I got for the even case. So we have to go through a few steps. If I take kappa squared plus L squared, right, why would I do that? It's not written anywhere in my solution at all. It's because somebody has gone through and found this substitution makes life easier. So if I take kappa squared plus L squared, I substitute for kappa, substitute for L, I get this here. That's kappa squared and L squared. And if I add these two together, the terms with the energy are going to subtract out, and I'm left with just this, which is the Z0 over A quantity squared. So now I've made a relationship that will relate kappa and L and Z0. Well, since Z is LA, I can take this and go a step further and say, let's divide everything. Let's divide everything by L, since it's kappa over L in my equation. And so I would have kappa, or over L squared, excuse me. So kappa squared over L squared is right here. L squared over L squared is just 1, so I replaced L squared over L squared with 1. And then Z0 over LA, all squared. I just divided everything by L squared. But that's going to be LA, that's Z. So I replace this box here with that. It seems like a lot of work, doesn't it? But what it's gotten me to is being able to rewrite my boundary condition in terms of one variable Z. One side's very simple, tangent of Z. The other side is not that complicated, square root of parentheses Z squared over Z quantity squared minus 1. And so now we take these and define, okay, blue is going to be this here. So I'm going to plot that in blue as a function of Z. And then I'm going to plot this here is actually, that might be green in color. It's hard to tell what the colors are. I'm going to assume that's green. I'm going to plot this function as well. And anytime where the green line and the blue line intersect, I have a solution. Now, then I take something like, well, I use spreadsheets when I do this. And I zero in on those values to find exactly where it crosses. When I say exactly, you just have to decide how many decimal places do I want, and you do your math so that you find that value. So the solutions for the even case are here, 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 and those are all the solutions in this graph. Now, what the graph actually looks like will depend on the depth of the energy well and the width of the energy well. So you could have only one solution, or you could have a very large number of solutions depending on the parameters of the well. But those are the even solutions, not all of the solutions, just the even ones. As you can tell, there's a second set of solutions. The textbook doesn't do the second set of solutions because that's one of the homework problems it assigns. So, of course, the textbook doesn't do the solution and then say, now for your homework, do the solution I just did. So we now have half of the solution. Any questions on how we did the half of the solution here?
Not really a question on how, but if we were given a homework or a test question like that, would we be expected to graph?
Okay. You would be expected, if you're given something like this, you would obviously never be expected to find the actual values of the intersections. But you could be asked something that would be, how do you solve this transcendental equation? And then you would say, using a numerical method or the graphical. I probably would say, how would you do it graphically? Because the graphical one is the one you can see and explain better. The numerical one is, well, you see that equation that I highlighted in yellow? I find the values of Z that make it equal or make it true. That's the explanation for the numerical. It's a little less explanatory, whereas the graphical makes it clear. So then you would have facsimiles of the graph. you wouldn't have the correct graph, because who's going to have their tangent curve correct, right? You know its shape, but exactly where it should be at some point, you get a few of the points, well, look, here's 90 degrees. I know what it is there. Here's 45 degrees. I know what it is there. But yeah. So you would just have something that's a rough shape. And it would be about the process, not about the solution, not about the actual values. Other questions about this? Have you had to solve a transcendental equation in any other class? Nope. So that's a new analysis method. Yay. Yeah, I wasn't happy when I learned to do it either, because it was new.
What exactly is a transcendental equation? Just one that can't be solved normally, analytically?
As far as I understand definitions, yes. I'm not a math professor, so if you go and ask one of the math professors, they might say, "Oh, that's such a physicist answer." Here's what it really means. Okay, so the graph shows the red lines. We won't worry about those right now. Now we're going to come back, and the normalization is how you get the actual value for your constants. It was nice and convenient that my constants canceled out here. I was able to eliminate the constants except for the energy. But now to get the constants in the Schrodinger equation, I can use my relationship between B and D. Either one of them will obviously work. And then solve using normalization integral for what it is. And here's where I said, and let me admit here, I hope I did the math right. Right? I do the integral from minus infinity to minus a of psi 1 mod squared, plus the integral from minus a to a of psi 2 mod squared, plus the integral from a to infinity of psi 3 mod squared, because this is the symmetric solution. I have the same thing for, well, even if it was the anti-symmetric, I'd still have the same thing for the integrals of psi mod squared outside of the box. So I combine those two together. That's where the 2 comes in the first one. Brought the constants out front, and I have that integral plus the integral inside, where again I brought the constants out. I trust that I did that integral right, and ended up with D is, and of course, what you've really solved for is D mod squared. So the square root of that, there's more than one answer to the square root of that, and I just take the positive real. Right? It's just, why not? You can take that positive real and multiply it by e to the I anything, and it's still a solution. But why not just choose e to the I 0? Make life easy. So that's the value I think is correct for D. I actually looked online real quick, couldn't find anyone who does it, because nobody ever worries about normalizing the equation at this. They worry about the quantum state for the energies. So moving on to the odd solution, the one that's not in the textbook, that's left for a homework problem. For the odd solution, then I'm going to have D is 0, because that corresponds to the even solution, the cosine term, and B is equal to minus F, so it's anti-symmetric. And with that set, I get, again, just 2 boundary conditions, and I take the lower one, divide by the upper one. Notice that cosine over sine is cotangent, and so the left side is exactly the same, minus kappa over L. There was a new minus sign, so is equal to minus cotangent of LA. So I have this solution for the odd case that's just like the solution for the even case, except for instead of tangent, it's minus cotangent. So I don't need to go and redo everything. That's going to be the transcendental equation I'm going to plot. So in the graph had minus cotangent plotted in red. Why? Because, well, that's what we found was minus cotangent of Z. So now we have additional solutions where the red line crosses the green line. And then they're just numbered in order from n equals 1 for the lowest energy and n equals, in this case, 6 for the highest energy for the crossing. So this has a total of 6 energy states available. If I were to change the dimensions or change the depth of the well, I could have more, I could have less. So that is the full solution for the problem. The second half, once you've done the first half, the second half is not very difficult because all that's different is changing it to minus cotangent and doing the same mechanism. But you have to have the first one under your belt, or else the second half is just as bewildering. What questions do you have about that?
So the number of energy states depends on the size of the well and the difference in potential, right? Yeah,
the depth of the well and the width of the well. Notice that our z, that variable, was defined as L times A, and L has the potential V in it, and of course A is the width of the well.
Right.
And so the shape of everything depends on those two parameters. And Z0 had to do with the potential as well, so it's both of them combined. Should I move on?
Yep.
I want to make sure that I don't leave you baffled and confused. So that's why I pause and ask. Okay, now problem 4 from the homework. Now that I've done this, problem 4 actually comes out to be a simpler thing because we're doing fundamentally the same thing we just did. We have 3 regions just like before. The only difference is the solution in the middle region looks a lot like the solutions in the regions 1 and 3. So we're going to have all the same things. Boundary condition 2 is going to be different because we have an infinite boundary. So here's what the potential function looks like. I don't even remember where I got this picture from, but I did not make it. So how many bound states does it possess? Well, I guessed 2 because I had one bound state with a single delta well. But that's not my answer, that's a guess. I have to solve the problem to get the actual answer. So using the same methods done with the single delta, I'm going to have the solutions in each of the 3 ranges. I didn't rewrite it here, and I wouldn't expect you to have to rewrite it here either. If you have a potential energy of 0, which is what you have everywhere the delta function doesn't exist, then you have your solution is, e to the I kappa x plus e to the minus I kappa x. If you're in region 1, you have to get rid of one of the terms. Region 3, you have to get rid of the other. In the middle region, you're going to have both because it doesn't go to plus or minus infinity. It's important to realize we threw away one of the solutions or set its coefficient to 0 because we had it blowing up at plus or minus infinity. If the region does not include plus or minus infinity, then you shouldn't have to do setting either of them set to 0. So just like in the last problem, we have here is our solution for the wave equation with a total of 5 unknowns. B, C, D, F, and of course, kappa, which depends on energy. So we now use the boundary conditions. And here I did the continuity. That is, the function must be continuous at each boundary to get the 2 boundary conditions. So those are the 2 boundary conditions for continuity. The first one evaluated at minus A, the second one evaluated at plus A. Then for our second one, instead of having a continuous derivative, I actually had to do that integral of the Schrodinger equation method that says the change in slope at the boundary is equal to minus 2m alpha over h bar squared times psi at the boundary. Now notice I put psi 1 at the boundary. I could have just as easily put psi 2 because this was the boundary between psi 1 and psi 2 and it has to be continuous. I chose psi 1 because it's shorter to write. Right, psi 1 only had one term. And so I get a new boundary condition there. and a boundary 2, similar boundary condition. So there's 4 boundary conditions just like before because we had 2 boundaries, each one having 2 conditions. So with those 4 boundary conditions, I summarized them here. And you'll notice that in this summary for the boundary conditions, for these 2, I had B on both sides of the equal sign, so I moved it across so I'd have B by, just one term with B. F on both sides, moved it across so I'd have just one term with F. And once again, this is the place where I find myself, I have to apply my symmetry conditions. Because I had a symmetrical potential function, then I'm going to have my solutions are either symmetric or anti-symmetric, so psi mod squared is symmetric. So I do each condition separately, just as before. Now, you can see that having gone through this more carefully makes the homework easier, right? So I will first go through the symmetric solution. So for the symmetric solution, I set B is equal to F. And so I just rewrote one of the upper equations and one of the lower equations, setting B equal to F and C equal to D. So this is the symmetric case of B equals F, C equals D. So there's only B and C. And since B is equal to C, where I had B e to the kappa A plus D e to the minus kappa A, it's just C times parentheses with a plus between them. So I take the lower one and divide it by the upper one, just like we just finished doing with the particle in the finite well. And I get a relationship. Now, you may not recognize this, but the right-hand side is tang, right? The hyperbolic tangent. Now, the difference in a hyperbolic tangent and tangent is, of course, tangent repeats over and over and over. The hyperbolic tangent doesn't. And so it turns out that when you solve this graph, whoops, I'm not even sure how that happened, but when you solve this graphically, you're only going to have one intersection. So you're only going to have one solution for the energy for the even case. We haven't gotten to the odd case yet, but for the even case, we're only going to have one solution. Now, tangent of 0 is 0, so we're always going to have one solution from this. And so it's a transcendental equation. Later on, we have to get a value for it, but right now there's one solution there, always one solution. Now we go to the anti-symmetric. For the anti-symmetric, that was the case where I only have 2 highlighters defined. One's black and one's yellow. Let me just go ahead and define another highlighter that's not black. So there is my conditions for the odd function. B is equal to minus F and C is equal to minus D for the anti-symmetric function solution. And so doing the anti-symmetric solution, I get, I get this and this, take the lower one, divide it by the upper one, and I get that as my solution equation. Just like before, the only real fundamental difference is this is hyperbolic instead of regular cotang. But hyperbolic cotang is not 0 at 0. It's infinite at 0. And so depending on the size of your well, you could have a situation where there's either no solution or there's one solution. So it depends on your parameters which one you get, which is why the next part said find the solutions for, and it gives you 2 different alphas. Depending on that alpha value, you would have 2 possible different cases. So we could have one solution, the even solution, or we could have 2 solutions, an even solution plus an odd solution. And that brings us to the last part. Find the allowed energies for, first, if alpha is h bar squared over ma. Well, if I substitute for alpha, then it just becomes 1 minus 2 over kappa is equal to minus hyperbolic cotangent of kappa A. If you do that numerically, Oh, wait, I got my symmetric and anti-symmetric backward here. The symmetric was the tangent one, and the anti-symmetric was the, and I'm pretty sure that oh boy, I copied and pasted poorly. I copied and pasted poorly. Yeah, that's just beautiful. There are two solutions to the first case, and one of these is correct and one of them is incorrect because of the whole copy paste thing. I have down here a solution that I copied from Physics Stack Exchange, where somebody worked the whole problem out. And so the solution should have been, the other one was minus 0.317 here. Or wait. Yeah, the solution should have been minus 0.615 and minus 0.317 for the even and odd. And
then you have a factor of 1/4 for the.
So I have, if this one up here that said symmetric had tangent in it, and this one down here that said anti-symmetric had cotangent, and then I had that 0.0 or 0.317 for the, I think it's for the odds, the anti-symmetric one, then I would have them correct. I can't believe I made a mistake at that point. Anyway, these should not be the same solution because one's tangent, one's cotangent. And that was a copy-paste error. It was past midnight by the time I got to this point. I'm going to take that as my reason. Then finally, if you go to the case of, and I got symmetric and anti-symmetric backward again here. If you take the second alpha that's given, oh boy, I didn't put in the 4 here either. Should have a 4 right there.
Out of curiosity,
Yeah.
where did the energy, where did the negative 0.614782 and the negative?
Okay, so being very honest, I took somebody else's solution on that because I didn't feel like making a spreadsheet. It would come from making a spreadsheet and doing the numerical analysis. The site I took it from, he did a graph, showed the graph gives you a solution in this region, and then from that graph he did the numerical solution to know where to start. And that's what I usually use if I make a spreadsheet. I make it so I have a large range. I look at where the crossing is, and then I zoom in on that crossing. So I put in things with a parameter, so I'm going to go up by like 0.1 each step. And then after I found where it is, I set my starting point and set the step value to like 0.0001 so that I could find it more accurately.
Okay, so we would graph the left side of the equation and graph the right side where they intersect is the energy levels.
That's correct. Where they intersect, it gives you the value for, you're plotting kappa A or both. Notice you have kappa A on both the left side and the right. Oh my goodness. This A here should be out here. I don't know how I thought that let's just say it was past midnight and I didn't get any sleep because I'd been on the red eye. Because yeah, I made a few mistakes here.
That's all good. It's much clearer than what it was. Yeah, all that matters.
But it's really embarrassing to have symmetric versus anti-symmetric crossed up and to be missing the A. You can't just cancel with magic. Yeah. So there you find that you have two solutions for the first case that was given, both the even and the odd. you have only the even solution for the second case, and there's the value I should have had instead of just leaving the 0.614782. This here should have been up there, and this here should have been a different number. Yeah. Yep. Can't really justify mistakes. They just happened. So that's how that whole problem worked. Now, yeah, I expected you to find a solution online to guide you through, but that's not as good as having me explain it, I hope. And that's the reason we teach these classes, instead of having you just read it online. Fine, So let's just quickly summarize the method that was used for both of these problems. So for both of these problems, we started by taking Schrodinger's equation and finding a solution in each of the distinct regions. Distinct regions occurred when we had a distinct change in the potential energy function. So we found the solution in each region. In both cases, we took the fact that it has to be normalizable to modify the solution, getting rid of one term in each of the regions that goes to infinity. Next, we applied boundary conditions. The boundary condition number one is a continuous function, never having a discontinuity. Boundary condition number two, if you had a finite potential energy, was that the derivative has to be continuous. So that's what we did for the finite well. For the delta function, because that's an infinite potential, we use the other variation on that was if you take the integral of the Schrodinger equation, you can find the jump discontinuity of the slope at the potential energy change. So it was the boundary conditions in both cases was the next step. And then the third step was to combine those boundary conditions along with normalization. Notice I didn't even worry about trying to normalize the last one because it didn't ask me about normalization. It was late at night. Obviously, I was already making mistakes. It would have just been more mistakes to go through the normalization process. I was able to then find my quantization relationship without having to normalize. And that's been true for every problem we've done so far. I could find my quantization relationship without having to normalize. But I had to normalize to find the last constant. So it turns out every single quantum physics actual problem we've done, and every one we're going to do in the future, is going to follow those same steps. So having those steps in your mind is a really important process for solving a quantum physics problem. All right, our time is done. One thing, did you guys both see the message I posted about the evaluation of the class so far? Yeah. Okay, so please make sure you do that. This is a trial class. We want to make sure, if you're like totally dissatisfied, we want to know why, so we can either fix it or abandon the idea.
Okay.
Yeah, and if the problem is the teacher, well, there's not that much fixing because I'm the only physics teacher here. All right, have a great day. Have a great vacation, Chris. I'll see you, India, on Wednesday. And I'm not going to assign a homework for Wednesday. We'll just be preparing for the exam. And I will not, because I'm going to give you a test on Monday without another official lecture, I won't have any questions on tunneling on this exam. I'll just move tunneling to the next exam.
Okay.
All right.